All right, so last two practice problems of these types here. Selenium, tetrachloride, valence electron count, that's the first thing we do. Selenium is good for 6. It's a chalcogen, 2 away from the nearest noble gas. Chlorine's a halogen, 1 away from the nearest noble gas, so it's good for 7. 7 times 4, there's 4 of them, 28, that gets you 34 valence electrons. Selenium is going to be the central atom. And so let's just put these together here. And let's try to satisfy the octet rule. And so the way we would do that, right, is just to give all the chlorines 8 valence electrons total by adding 3 lone pairs, 2, 4, 6, 8. Remember, a bond is good for 2. So each of these chlorines has 8. 8 times 4, that's 32. Where are we going to, we have 34 valence electrons. So we have 2 more valence electrons unaccounted for. We're forced to put those on the central atom. That's okay, because selenium is row 3 on the periodic table or lower. And so you can do that. It's violating the octet rule, but there's no other choice, right? This isn't like a super stable molecule, but it exists. Violating the octet rule usually isn't super stable. But, you know, this is all we can do. So SECl4, there's our Lewis structure. Now let's ask for, you know, things about the shape and the steric number and geometry. Steric number is number of bonding sites plus number of lone pairs. 1, 2, 3, 4. 4 bonding sites and 1 lone pair. That means I'm going to have a steric number of 5. Steric geometry, therefore, when you have 5, is the pentagonal. Sorry, not pentagonal. Sorry, guys. Thinking about steric geometry 7, which is not something you guys learn. Trigonal Bi-Pyramidal. 7, by the way, happens to be pentagonal bipyramidal, which we don't go over in this course, but you know, there's cool higher steric numbers out there. Trigonal Bi-Pyramidal. Trigonal Bi-Pyramidal, where does that name come from? Not super hard to visualize. It's a triangle, okay, but it's a triangle that is squashed because it's like this. It's in the plane. It's out of the plane, okay? So going like this. And then you're going to have 2 points, the bipyramid, on top and on bottom. So it sort of looks like there's like that. Okay. But anyway, that's the steric geometry. Molecular geometry, well, we have 1 lone pair here. And so 1 lone pair means that essentially we have removed one of these pyramids. And so this kind of has a funny name. It's called seesaw. But that's the molecular geometry, okay? It's just removing this point. Bond angles. Bond angles for a trigonal bipyramid. Those are going to be, there's 2 of them. You have that center triangle, and you have, this is a harder type of problem, guys. So, you know, don't worry too much about the bond angles for this. But you have 2 of them. You can imagine that center triangle, well, it's a triangle. That idealize is 120 degrees, and then you have the bond angle between the pyramids. That's 90 degrees. But you have a lone pair here, right? And so the lone pair makes these less than the ideal, okay? Let's do hybridization on the central atom. Selenium, it has a steric number of 5, so it's going to be sp3d. 1, 2, and then 3 orbitals there. Next one, SeO2. Valence electrons, 6 for selenium, and 6 for oxygen, but there's 2 of them. It's going to get me 18 valence electrons. Selenium is less electronegative, so we're going to put it in the center. We're going to go 2, 4, 6, 8, and we're going to do 2, 4, 6, 8. So that gets us octet rules for the oxygen satisfied. and we're looking good. But our central atom does not have the octet rule satisfied. It only has 2, 4 valence electrons. We have 16 total valence electrons, 2, 4, 6, 8, 10, 12, 14, 16 I counted for. We have 18 we need to put down, so we can put 2 more. That still doesn't help selenium quite enough because it's at 2, 4, 6. So that tells us, right, that one of these lone pairs is going to have to turn into a double bond. And so that now is happy. Oxygen's at 2, 4, 6, 8. Selenium's at 2, 4, 6, 8. Hopefully you can see with some practice with these that you could also write this a different resonance structure. Remember, we call these resonance structures when there's 2 different ways of drawing it. This is just a different way of drawing the resonance structure, where now the oxygen on the left has the double bond. And so really, you know, the effective bond length here is, for each of these bonds, is kind of like a 1.5 bond. And because, you know, it's equally valid to write a double bond there, or it's equally valid to write a single bond there. So the bond order is actually in between. Okay, so it's intermediate of strength, intermediate of length of a single and double bond. That's cool. Let's do steric number of central atom. Steric number of central atom is number of bonding sites, right? 1, 2 plus number of lone pairs, 1 lone pair. So that gets us steric number of 3. That gets us steric geometry. By the way, that gets us sp2 for the hybridization. Steric, right, 3 orbitals. Steric geometry is going to be therefore trigonal planar, right? 3 points. Best way to put them farthest apart from one another is to put them in a triangle. Just a normal triangle. Molecular geometry, we do have a lone pair there. And so it's a triangle, but we've gotten rid of, and there's a central atom. We've gotten rid of one of these vertices, because it's just mostly free space, electrons there. And so our structure in the end is not a line, it is bent. Idealized bond angle for trigonal planar is 120 degrees, equilateral triangle. But it is going to be bent, so that means it's less than 120 degrees because of the extra size, so to speak, of the lone pair. It takes up more space.